The US military recently announced a program to create the holy grail of spy satellites called Ground Moving Target Indicator Synthetic Aperture Radar. They have already launched a prototype satellite, and even commercial providers now have moving target indicator and VideoSAR products on the marketplace. An even more ambitious program is an air moving target indicator radar constellation, and together these would replace the Air Force's airborne radar fleet and allow for tracking any vehicle through clouds anywhere and anytime. So today we will be calculating what these satellites would need to look like and how powerful this constellation could be. First, let's explain why we use synthetic aperture radar and how it works. You can't form good images with an ordinary radar because it only has one angular pixel with very low resolution. In a camera, there are millions of pixels on the focal plane, so it will record the light at thousands of angles in each direction from the bore site to form an image. A static radar can measure range, but it can only image one angular pixel at a time, so it would have to drag the radar beam across the entire scene to form an image. The angular resolution equation for radar is also a function of wavelength. So an X-band radar has 45,000 times worse resolution as that of an optical camera. For example, for an antenna the same size as a phone camera, which is smaller than an X-band wavelength of 3 centimeters, the resolution would be larger than the distance to the target or scene. Now, if only we could have an aperture that was several kilometers wide, then we could have the same resolution as an optical camera. Well, it turns out this is possible, and it's called a synthetic aperture. We will start by showing a synthetic aperture formed by an aircraft in Stripmap mode. Here the SAR antenna will move across a scene, and the size of the synthetic aperture will be the physical width of the antenna beam projected onto the ground. As the radar moves across the scene, a Doppler effect is produced. Return signals from objects the radar moves towards are shifted to higher frequencies, and the signals from objects the radar moves away from are shifted to lower frequencies. Therefore, the synthetic aperture is formed in the direction of motion, which is called the azimuth or cross-range axis. The range of frequencies created by this Doppler shift is called the Doppler bandwidth, and it is determined by the speed of the platform and the beam width of the radar. The radar needs to pulse at a frequency called the pulse repetition frequency, or PRF, greater than the Doppler bandwidth. If the PRF is lower than this, the undersampling produces Doppler ambiguity that will create ghosting like you see here for frequency domain processing. Counterintuitively, the azimuth resolution in Stripmap mode is limited by how small your physical antenna aperture is in the azimuth direction, since a smaller antenna produces a wider beam and a larger synthetic aperture. In the angular elevation direction, there is no synthetic aperture, so we use range from the radar for our other axis. So in every pulse, the antenna receives return signals at different times depending on the range, and at different frequencies depending on the position in the azimuth direction. The radar will record thousands of pulses to form what is called the raw phase history. The rows of fast time are the time domain return signal from each pulse. The columns of slow time are formed by stacking many pulse returns over several seconds. Using range as an axis of an image is why SAR images look so strange compared to photos. Here I will show examples of the so-called artifacts that this produces. Image formation with range and azimuth axes is also why SAR platforms usually only work at grazing angles between 30 and 60 degrees. If you try to use SAR directly above the target, all of the ground clutter will fall into the same range bin and you will not be able to resolve the scene. The resolution in the range direction is independent of antenna size or distance from the target, and it will depend on the bandwidth of the transmitted signal. SAR platforms use a chirp as their radar pulse, and this is a signal with linearly increasing frequency. You can see here that the range resolutions can be very small, and this is really only limited by practical and legal constraints such as the FCC in the United States. The largest allocation now is 1200 megahertz, but in a time of war, the military could go higher and avoid interference by emitting below the noise floor. We will be sticking to vehicle models made from point targets in the simulations. I tried to simulate a full 3D scene, but I found out the hard way that it is completely impossible to ray trace thousands of pulses like this on my consumer GPU. And this is why you won't find any code for complex 3D simulations of SAR on the internet. So just keep in mind that point targets are brighter than distributed targets, and they will not have shadows, and they will not have all of the same artifacts that you would see in a normal image. Also in my simulations, I will not be simulating the rotation of the Earth, and I'm also going to assume that I always have perfect position information about my radar. Now let's start simulating some SAR data, and we will start with a scenario of an aircraft in Stripmap mode. The aircraft will fly for 15 seconds, and this is called the coherent processing interval, or the CPI, to form a synthetic aperture of 2,500 meters. I will assume these specifications for our aircraft scenario. There are dozens of different SAR imaging algorithms for different applications, and I will be using the range Doppler algorithm as a simple example to explain Stripmap imaging. We start with our raw phase history that is collected across the entire synthetic aperture. The first step is pulse compression, which focuses the chirp into a sharp signal and filters out noise. This is achieved with a matched filter, which filters the noisy combined signal for the expected chirp signal. In doing so, it amplifies the weak radar signal and suppresses noise. The next step is a Fourier transform along the azimuth axis. A Fourier transform will transform a time or spatial domain signal into its component frequencies in the frequency domain. We can convert back from the frequency domain using an inverse Fourier transform. Also note that the values are complex, so they have real and imaginary values, and I'm just showing the magnitude here and not the phase. You can see that after the Fourier transform, the slow time axis is converted into the Doppler axis, showing the received signal based on the frequency. However, since the radar range changes over time, the fast time axis is not accurately converted to target range initially. This results in a curve in our data. As shown in this diagram, the slant range to the target at any given time differs from the minimum range R0. To correct this and straighten it out, we apply range cell migration correction using an interpolation based on the known trajectory of the aircraft or satellite. Now that the range axis is corrected, we can move on to the next step. At this point, the response from each point target is still spread out over the slow time axis, since the Doppler shift changes over time for each target with the radar's motion. The signals can be compressed by applying a match filter, this time in the azimuth direction. The match filter in this case will be filtering for a specific phase shift pattern that depends on the target's minimum range that range cell migration correction aligns it with. When we compare this to the range compression match filter, you can see that the range filter has a magnitude term and it doesn't depend on range. This means that each range bin needs its own match filter, whereas for pulse compression, we use the same match filter for each pulse. Also, the magnitude does not change for the azimuth compression match filter. When we compare the phase of steps 3 and 4, however, you can see how it is working by filtering only the phase. Lastly, we perform an inverse Fourier transform in the azimuth direction to get back to the range and azimuth dimensions. And after zooming in, we can see our focused point targets in the shape of a destroyer. So far, I've showed the magnitude in linear terms, but in decibel view, you can see the noise and side lobe artifacts that are lower magnitudes. Stripmap imaging will produce major artifacts for any moving targets. For an object moving in the azimuth direction, the image will be smeared since its position changes over the 15-second coherent processing interval. For objects moving in the range direction, this produces a Doppler shift that will shift the object in the azimuth direction. Diagonal movement has both artifacts. Also note that shadows and wakes from ships will not be shifted in the same way. Now I'll show the range Doppler algorithm for a SAR satellite scenario. The satellite moves at 7 kilometers per second, so the synthetic aperture is formed in just 1 second. I will assume these specifications for our satellite scenario based on commercial SAR satellites. Another difference is that since the slant range is 25 times as far, and because the radar range equation is inversely proportional to range to the power of 4, the free space loss is 55 decibels more for the satellite compared to the aircraft scenario. Because of this, the signal starts below the noise floor, and you can see the power of the match filter in action here. I will show this one in decibel values, and you can see here that we have 7,000 by 14,000 data points, and each of these has 128 bits. So this works out to 6 gigabytes of data collected in just 1 second. And here you can see how the image is focused, again, over the steps of the range Doppler algorithm. When I switch back to linear, you can recognize the destroyer. And here are the movement artifacts for this scenario. You will notice that for a moving ship, the azimuth blurring is much less noticeable since the CPI is only 1 second instead of 15, and you can make out the layover artifact from the sideways viewing angle. Motion in the range direction produces an azimuth shift similar to the plane scenario. To overcome these artifacts and to track moving objects, we can change our collection mode and our processing algorithm. We can change to spotlight mode instead of Stripmap, and then change the algorithm to time domain back projection instead of the range Doppler algorithm. In spotlight mode, the radar focuses on one target as it moves, and the ideal resolution is now determined by the SAR angle, or the angle formed by the motion of the radar, instead of the size of the antenna. This allows for larger antennas with higher gain and smaller swaths, and it also can enable shorter coherent processing intervals. I'll now briefly explain how time domain back projection works. The first step is pulse compression of the chirp signal just as we discussed earlier. Next, we create a two-dimensional plane of pixels, usually on the surface of the Earth, as our target area. Using the known trajectory of the radar and the rotation of the Earth, we can calculate the range at every single pulse in slow time. Each pixel on the plane will then have its own unique range profile. When we zoom in, our range bins are discrete values that do not match the exact values for the range profile of each pixel. So we interpolate to give better estimates for the complex return signal for each pixel at each pulse. The final step is to simply sum the interpolated signal across all pulses for each pixel. We also need to add a phase correction term to amplify signals with the expected phase shift of the carrier signal. This will act as a filter for the exact range profile of each pixel and suppress signals originating from other pixels with destructive interference. In the final image, you will notice that the point targets appear smaller because the azimuth resolution is much higher than in my Stripmap simulation. This algorithm is mathematically more simple than most of the frequency domain processing algorithms, but it requires much more computation. It has a number of advantages, like the ones listed in this thesis paper, and the most important for tracking vehicles are the ability to easily compensate for motion and the ability to avoid serious effects from target-induced Doppler ambiguity. VideoSAR uses the same back projection algorithm, but it splits a longer coherent processing interval into multiple overlapping coherent processing intervals that will form a time series. In my scenario, I split a 5-second collection interval into 50 frames, and each frame is generated over 0.5 seconds. The only specification I will change for this demo is the antenna diameter is set to make the scene size the same size as the main beam swath, and this works out to 8 meters for our aircraft scene. I'm doing this just for demonstration to have a close-up of the vehicles and to avoid stretch processing, which means sampling only a subset of the chirp to focus on a smaller scene. If you generate these videos with stretch processing and moving target back projection, you get full brightness wrapped ghost artifacts like these caused by the frequency domain processing. In reality, the antenna would be smaller and the swath would be much wider. We will start with the same satellite scenario, but this time in spotlight mode. We will have the destroyer moving in the same directions, and I am also adding a fighter jet at cruising speed and at Mach 1.5, and a stealth fighter jet as well. When we first generate these videos, the artifacts are so severe that in many cases, you cannot see the signal of the targets above the noise. So I will be turning off noise and changing to decibel view to show what they look like. In standard spotlight back projection, motion in the azimuth dimension still causes smearing, and motion in the range dimension causes more severe smearing and a displacement that changes based on the squint angle. The squint angle is the angle of the beam from the perpendicular axis to the radar's plane of motion. Often the target will be displaced outside of the image, which leaves only weak signals from the side lobes and looks like a very severe artifact. When this happens in frequency domain processing, instead of just leaving the scene, the target will actually be wrapped back into the same image. Here are some videos from ICEYE that show real VideoSAR from their satellites, and you can see some of these artifacts in the moving vehicles within these scenes. We can correct these effects with moving target back projection, or MBP. This algorithm is nearly the same as TDBP, but the stable grid of pixels is now moving. So both the estimated radar trajectory and the expected target trajectory are accounted for in the range calculation. This will also distort all the clutter and anything that is not moving at the expected velocity. Now I'll show the corrected videos using MBP. In my simulation, I am using the exact position and velocity values, so the targets are nearly perfectly focused. In reality, to have a working custodial tracking constellation, we would need to use autofocus algorithms to correct our position and velocity errors. At a high level, these algorithms can estimate errors based on the artifacts or generate multiple frames in parallel with different assumptions and determine the direction of errors based on which frames have improved or worsened artifacts. You can even autofocus several different targets with the same spotlight swath at the same time, since the data collection remains exactly the same. And with a phased array, you can change the location of the spotlight very quickly to monitor multiple targets in distant locations. This is an idealized simulation, and we would probably expect a lower signal-noise ratio, position error for our platform, and position error for our targets, so the images would not be this perfect. But even poor SAR videos that are very hard to interpret for humans can still be easy to interpret for image processing and machine learning algorithms. I can imagine a closed-loop system with noise filtering, autofocus, change detection, and then machine learning-based tracking that would be very effective and use far less compute than the back projection itself. Another factor is shadow tracking. Because shadows are not real objects and are just the absence of a return signal, they won't be affected by motion artifacts, and they can be used to estimate the position and velocity of the object that produced them based on the radar geometry. The only real downside to tracking shadows is that sometimes tall objects can lay over into the range bin that the shadow is in and obscure it. So in like city situations or maybe forests, this could potentially be an issue. In my simulation here, you can faintly see the stealth fighter, and this may be somewhat unrealistic because the radar cross-section of the point targets would be spread out over the whole aircraft and would be much darker than the clutter underneath. To track these, you'd probably need to either track the shadow, which would be the same shadow as the ordinary fighter jet, or use some form of clutter suppression. This can be done simply by subtracting the clutter that is stable between frames, or with variations of space-time adaptive processing that we will discuss later in this video. One more option is to have a beam that is narrow enough in the elevation direction that it will have a time delay between targets at high altitudes and all of the main lobe clutter on the ground. Depending on the geometry and the pulse repetition frequency, this could allow you to focus on the return of a stealth fighter at a high altitude with only noise and no clutter. In a future moving target indication constellation, VideoSAR would allow for custodial tracking of targets. Spotlight mode allows for greater squint angles, so you can have fairly good coverage. However, even with generous look angle and squint angle limits, you still need roughly 500 satellites at 500 kilometers to have persistent tracking. You can increase the altitude to improve the coverage, but this will decrease your signal-to-noise ratio and increase your swath width, requiring more processing. But remember that this algorithm creates videos for relatively small areas, and it also relies on having very good estimates for position and velocity of the targets to properly focus them. Doing the initial detection for very slow-moving ground targets and very fast-moving air targets over very wide areas is the more challenging problem, and this will need to be overcome with a more complex system of SAR satellites. The ideal solution is not obvious, but I will explain all of the systems and upgrades that are being considered. The first upgrade is high-resolution wide swath mode. Traditional Stripmap has several problems that make it ineffective for wide area moving target indication. The first problem is known as the Doppler dilemma. Smaller antennas produce wider beams with better resolution, but they also have a greater Doppler bandwidth, so they require a much higher pulse repetition frequency to prevent Doppler ambiguity. For a resolution of 25 centimeters, this requires a pulse repetition frequency of 30,000 hertz. The PRF, however, must also be kept low enough to avoid eclipsing and range ambiguities. The limitations here are the distance from the targets and the size of the swath in the range direction, since a wider beam width in the elevation direction spreads the return signal over a longer period of time and can create overlapping receive signals from different pulses. In existing commercial SAR satellites, this requires a pulse repetition frequency of around 6,000 Hz or even less. Another problem is that the signal-to-noise ratio is very low because both the transmit and receive antennas have a very wide beam width in both angular directions, and they have a very low gain as a result. Multi-channel arrays, sometimes called single input multiple output, mitigate the Doppler bandwidth problems. In this configuration, a phased array will transmit a broad pulse. Then on receive, the antenna will be split into multiple sub-apertures. These multi-channel antennas split the beam into n separate sub-beams, and in doing so, they also split the Doppler bandwidth into n partitions. Since each sub-beam still pulses at the physical PRF, this creates an effective PRF of n times PRF when the signals from each sub-antenna are combined. Note that we cannot simply split the beam into hundreds of sub-apertures because each additional sub-aperture will require additional hardware plus exponentially more computing power for combining the beams. Also note that this effective PRF will not change the required PRF for unambiguously detecting very fast-moving aircraft because the Doppler shift that's induced by this will only be detected by one of these sub-apertures. So this upgrade mitigates the Doppler dilemma, and it allows for both better resolution and wider swaths in the azimuth direction. However, multi-channel does not decrease the PRF requirements for moving targets. Moving targets in SAR are subject to the maximum unambiguous radial velocity. Above this, the Doppler shift of the moving object causes aliasing. In the design for my demos using a 6,000 Hz PRF, this works out to 45 meters per second, which is good enough for ships and ground vehicles, but not aircraft. The only reason the aircraft were focused in my VideoSAR demo was because that was all time domain processing. In frequency domain processing, the velocity of the target can alias and appear lower than it actually is, and then also the azimuth shift can also be inaccurate. For wide swath imaging, this is even more catastrophic. So a plane moving at Mach 1 in the radial direction for an X-band antenna would require a 45,000 Hz physical PRF. Most objects will only have a small component of the velocity in the radial direction, and you can have a dense constellation with different geometries, but a much higher than usual PRF is still required for a reliable air moving target indication. Theoretically, there are some advanced designs and algorithms that you can use to resolve ambiguities, but in general, you just want to have a PRF high enough to avoid this. The first upgrade that will help with PRF is called digital beamforming scan on receive. Digital beamforming of a phased array allows the beam to be shaped into a sharp pencil beam that is steered across the Earth very quickly to receive the instantaneous ground echo. This masks return signals from off-target ranges and other pulses and allows for a higher PRF. It also improves the gain of the receive antenna, improving the signal-to-noise ratio. So scan on receive will improve the range ambiguity limitations, and this will allow for higher PRFs in each of the sub-apertures or channels. An early adopter of digital beamforming scan on receive technology is the NASA NISAR satellite, which was launched in July 2025. Here I show a video from NASA, and you can see in this animation how it is working. A way to directly improve the PRF is with multiple input and multiple output antenna arrays that produce different types of pulses that will not interfere with each other. The simplest way to do this is with frequency division, which means sending chirps in different frequency bands, and the downside of this is that it requires more bandwidth, assuming you keep your range resolution constant. If you sacrifice your range resolution and lower the bandwidth, then you can increase your PRF drastically. Another technique is code division, where the radar sends up chirps with increasing frequency and then down chirps with decreasing frequency. These have very little interference after match filtering. There are also some more complex space and time division, multiple input, multiple output strategies. One more little upgrade is to have dedicated transmit and dedicated receive antennas, so then the receive antennas can spend slightly more time listening. They won't have as much interference from transmitting the signal. All of these upgrades will be used to achieve a very wide swath with high resolution. On the screen now is a simulated view of a constellation of these satellites, and similar to my spotlight demo, we will need around 500 satellites to produce ideal revisit times of a few minutes, which would be the near persistent detection required to tip off the VideoSAR mode satellites of high priority targets. I assume that this mode will not use any squinted geometries and that the azimuth swath will be 250 kilometers across, which is the azimuth swath of NISAR. The range swath would only fill part of the yellow region I animate, and this would be adjustable, and of course this would just be on one side of the satellite at any given time. So the revisit time for the entire Earth would be much longer than for a given high priority target area. The size of the swath would also become smaller in the range dimension for a high PRF air moving target indicator mode. A ground moving target indicator mode could have a much wider range swath, and the azimuth swath could also be reduced to create redundancy for space-time adaptive processing. I should also mention that these could be very flexible satellites that could switch between a combination of many different modes, including the VideoSAR spotlight mode I showed earlier. This brings us to the last piece of the puzzle, which is the category of space-time adaptive processing. This will allow us to separate the moving targets from the stationary clutter through redundant sampling with multiple receive antennas or sub-apertures. Without space-time adaptive processing, it is very difficult to properly detect moving targets. In a monostatic SAR scenario, we have the dimensions of time and range. When we add redundant sampling in the space dimension with bistatic or multistatic antennas, we now have time, range, and space. The simplest version of this is a long-track interferometry, where you interfere the receive signals of two sub-apertures that are separated by a short distance. In practice, you do this by multiplying the values in the final single-look complex image for one antenna with the complex conjugate of the image from the other antenna. Stationary clutter does not produce a phase shift in the interferogram, but moving objects will. The phase shifts shown in the interferometer directly correlate to the radial velocity of the objects. It follows this formula, and the effective baseline is generally the distance between the antenna phase centers, but this can change based on the transmitter setup, and multiple input, multiple output can also increase the effective baseline. If we know the radial velocity, we can account for the azimuth displacement as well to find the real location. If the radial velocity exceeds the maximum unambiguous radial velocity, however, then the phase shown in the interferogram will wrap back around and it will appear slower than it really is. Sometimes targets can travel fast enough to wrap back to zero phase, and this is called the blind speed, where it won't be detected. The wrapping also affects the azimuth displacement that is caused by radial motion. One of the few ways to detect blind speeds and ambiguities in general is by using two or more pulse repetition frequencies. For a non-alias target, the position and velocity should look the same at different PRF settings. For an alias target, however, the PRF will shift the phase and apparent position, and you can use this to recover information about the target. Many existing satellites can use a long-track interferometry, including TerraSAR X and its companion satellite Tandem X. These satellites fly in a formation that will also sometimes allow for cross-track interferometry, which enables measuring elevation of the Earth. And they can also be aligned along track, which forms a very long baseline, along with the short baselines on each satellite. The advantage of longer baselines is detecting very slow motion, which is better for moving ground targets versus moving air targets. We already discussed the maximum unambiguous velocity, but there is also a minimum detectable velocity. If your target is moving too slow, the phase shift is so small that it blends in with the small phase shifts from noise and of the clutter that is not moving. The minimum detectable velocity follows this general formula, which relies on the effective baseline. With a 1 meter baseline and some basic assumptions, this equates to around 2 meters per second. So a very small baseline antenna design would not detect soldiers walking around on the ground, for example. There is also an along-track interferometry ambiguous velocity that depends on your baseline spacing. This is distinct from the maximum unambiguous radial velocity that depends on PRF. This one will only cause phase wrapping and ambiguities of the phase, so it is much more manageable. When we look at the velocity term in our ATI radial velocity equation, it has a phase term. Phase shifts offset by a full wavelength or more will therefore alias, and the true phase shift will be ambiguous. We can then solve for the velocity that causes this aliasing. For my scenario, the baseline must be smaller than 17 centimeters to unambiguously sample targets moving at Mach 1 or faster radially. So for the bistatic case with just one baseline, we have a dilemma with the trade-off between detecting slow targets and unambiguously detecting fast targets. We can solve this dilemma and this specific ambiguity problem by using 2 or more baselines with the Chinese remainder theorem. This theorem starts with our known values, which are the lengths of the baselines and the phase shifts from each baseline. I chose 20 centimeters for the smallest baseline, which normally aliases targets above 285 meters per second. We want to solve for the radial velocity. Next, we set up our 2 equations by filling in the known values into our radial velocity equation. K1 and K2 are unknown, but they must be integer values. We now have 2 equations and 3 unknowns, and after adding our realistic constraint for the velocity, we have 3 constraints. After testing a grid of integers, I have 2 solutions within my constraint of 500 meters per second. The simplest way to solve is to add a third baseline, and you can test your candidates to see if they match with any integers. It is important to have independent baselines. If I choose 40 centimeters, this is sampling the same frequencies as 20 centimeters, and it remains ambiguous. Choosing 45 centimeters is not a factor of 5 meters or 20 centimeters, and it gives us a nice clean answer. Our target was moving at the speed of sound, 343 meters per second. This radial velocity would have been incorrectly calculated at negative 227 meters per second if we had only used the 20 centimeter baseline. As more baselines are added, you can better resolve ambiguities and achieve higher performance. This same algorithm is also used in the multi-PRF ambiguity detection that I discussed earlier. Theoretically, the arrangement of baselines I show here would give you detection all the way from 36 centimeters per second to well above 285 meters per second. In reality, we are still constrained by the PRF for the maximum unambiguous velocity. Another design is displaced phase center antenna. In this setup, the effective baseline is spaced the exact distance that the platform travels in one pulse repetition interval. The second antenna will then receive the same spatial response from the ground clutter, so when the complex signals are subtracted, you are left with only the moving targets, which will have phase shifts. After the clutter is canceled out from the subtraction, you can easily detect moving targets in the scene. This is more effective than the interferometry operation at detecting slow-moving targets and suppressing clutter, but it does not give direct radial velocity estimations. You also need to have very precise alignment and velocity measurements for your radar, and the baseline would need to compensate for Earth's motion that changes with latitude. This is difficult but doable on a spacecraft, especially with modern metrology and very fine actuators that we already use for telescopes. Overall, DPCA is very useful and can save a lot of computation, especially if you want to simply detect targets for other systems to analyze further. And you can use the same antenna setup for both along-track interferometry and DPCA and do hybrid processing. I will now simulate this in Python using our satellite scenario and 2 antennas each spaced 1.28 meters from a central emitter antenna. This image is from the first antenna, and I've placed 5,000 bright stationary targets throughout the scene that will simulate the clutter. Starting with ATI, when I generate the interferogram using the second image, all the clutter disappears and the phase shift is about 1 radian. When I plug in some rough numbers, this gives us an accurate radial velocity, and then we can use this to calculate the azimuth shift and mark the ship at its correct position, which is 0 meters in the cross-range direction. You can also see how small the phase range is here based on the 1.28 meter baseline. You may notice that this 45 meters per second limit perfectly matches our PRF limited velocity, and this is because the effective baseline length is calculated using the PRF to meet the DPCA condition. The ship is only moving 15 meters per second, so it is 1/3 of the way through the range that goes up to 45 meters per second. If I simulated the fighter jet here, the phase would be aliased and we would calculate the wrong position and velocity. I can also use the same antennas for DPCA clutter cancellation. Here are the magnitudes and phases of the complex images from the 2 antennae and the resulting DPCA image without any clutter visible. Here I've zoomed in on a single stationary target and a single moving target so you can see how it is working. The phase is nearly identical between the 2 antennas for the stationary target, but it looks completely different for the moving target. This leaves a large residual value after subtracting the complex numbers for the moving target. So from what I've shown, it seems like these 2 methods would be sufficient, but in reality they are far from ideal, especially for very slow and very fast moving targets. One reason is that in real conditions, clutter will form a broad Doppler spread because of Earth rotation, error, and other factors. This creates some major challenges for slow object detection over very wide scenes that DPCA alone will struggle with. For small and fast targets, we need a better signal-to-noise ratio than a long-track interferometry can provide, and ideally, we want to use some more advanced techniques for ambiguity resolution, sparse sampling, and knowledge-aided processing. These improvements are only achievable with full space-time adaptive processing, and this is a specific technique within the STAP category. You can think of this as the big brother to DPCA because this will typically use 3 or more similarly spaced phase centers, and it will suppress the clutter, noise, and interference using correlations between these antennas that will change over time. By the way, I'll be using a lot of graphics from this video in this section, so check it out if you want more detail on space-time adaptive processing. One thing to note is that STAP mode acts more like a static early warning radar than a synthetic aperture imaging satellite. The range needs to be somewhat constant over the CPI, so because of this, the CPIs are usually very short. We will use an example where the CPI lasts only 15 pulses. I will also assume we are using 4 antennas. Performance increases with more spatial sampling, but space-time adaptive processing can work well with just 2 or 3 antennas. We start with our data cube. Here I assume that we have 4 phase centers, so there are 4 sets of range and time bins in the space dimension. We are also just using a tiny fraction of a second in the time axis. The first step, as always, is to pulse compress our data. At this point, we can choose between full STAP, post-Doppler STAP, and a range of other optimizations. Transforming into the frequency domain at this point tremendously lowers the amount of compute needed, but I will just stick to explaining full STAP since this is the mathematically ideal method that would have the best performance. Now we're going to zoom in on a single range cell to explain how this works. What you see here is our cell under test. There are 15 pulses sampled over 4 antennas, so 60 values per range bin. The next step is using all of the surrounding range bin as a model for clutter and noise. We ignore the cells next to us so that we are not modeling our own cell's leaked energy as clutter. Then we define all the range bins surrounding our cell as training data that we will assume as noise and stationary clutter. Here we can also insert knowledge-aided STAP techniques, which will augment the training data using known information like digital elevation maps, locations of man-made objects, moving clutter or other moving targets, and so on. This will be easier to do with a giant constellation of SAR satellites recording the clutter all the time, and you can prioritize it for regions of interest. Next, we will compute a covariance matrix using all of that training data. Each pulse antenna pair appears once on each axis, and all of the training range bins are used to compute a covariance with every other pulse antenna pair. The clutter signal does not change significantly between adjacent antennas or adjacent pulses, so it forms the highly correlated clutter ridge, along the diagonal axis. Because we want to suppress the clutter, we compute the inverse of this covariance matrix to null signals that match these correlation patterns. Then we will apply velocity filters to this specific range cell. These are predetermined filters, and they each search for a specific velocity using the multiple pulses and angle using digital beam steering with the multiple antennas. Each filter will form a steering vector S. Each steering vector is applied to the inverse covariance matrix to form a weight vector that will maximize the signal to interference plus noise ratio for a target matching the filter's conditions. This is then applied to the data within our cell under test to give a value for how much it matches the filter. And we can use a simple threshold or more advanced algorithms using multiple filters to detect a target. The final result is the ideal suppression of the clutter ridge so that we can detect targets that were hiding within the clutter. There are many more variations of space-time adaptive processing, including imaging STAP and interferometric STAP, which are more similar to a long-track interferometry. So the future ground-moving target and air-moving target indication constellation will need to use a lot of space-time adaptive processing to find very slow targets and very fast targets over these very wide areas. The constellation could operate using the techniques I've described so far. You could use high-resolution wide swath techniques, space-time adaptive processing for detection, and then VideoSAR spotlight modes for custodial tracking, and this would all be very impressive. But an even more ambitious idea, which is the real holy grail, would be a multi-static distributed constellation of radar satellites. This concept takes every idea that we have discussed so far to the next level, and it works by separating the transmit and receive radar satellites. For single satellite SAR, the transmit and receive antennas are on the same platform. In distributed SAR, you need just one transmit antenna, then you can receive the same signal with multiple formation flying satellites, or even a giant swarm of satellites, which will give you synthetic apertures and interferometric baselines in many different directions. If you are really crazy, you could even have multiple transmit antennas, or put the transmitter in geostationary orbit, where it can produce a response from the ground that will be consistent over time. When we consider our potential data cube, the diversity can be much more rich. We can now have baselines in the azimuth and elevation direction for a given direction of motion, and we can also form synthetic apertures in multiple different directions. Let's go through all the implications, starting with spotlight mode and VideoSAR. First of all, this can make your custodial tracking constellation dramatically better and cheaper. I showed you how you only need around 500 transmitters to cover the entire Earth, and after that you can add an unlimited number of receiver satellites. These would be much cheaper and they would not need very much power at all. They would just need a large phased array antenna, and then the demodulating and digital processing equipment, and then they would need a laser link to send all of the raw data to a central processing satellite. It's also possible that you could just amplify the raw RF signal and beam it to the central satellite, but this would cause a lot of problems. So I think these simple receive satellites could be as cheap or maybe even cheaper than a Starlink satellite, and launch costs are going to continue to go down. If you had 9,000 satellites like this, it would look like this, where you could have 20 satellites tracking a target at the same time, and it would be the most overpowered thing ever. Achieving this requires some complicated beam steering, but the back projection would be the same computation, and this would actually be even stronger because you would get specular reflections from stealth fighters, which are designed to reflect energy away from the emitter. Also, this would allow for 3D back projection, which is also basically the same computation, but now we calculate 3D voxels instead of 2D pixels. This is usually called circular SAR because aircraft will achieve this by flying around a target in a circle. There is also a 3D imaging technique in the frequency domain called tomographic SAR. This is normally done through stacking data from multiple passes of the same satellite, but a formation of satellites spaced out in the elevation or cross-track dimension could do this in near real time. Next, we have the concept of a very large STAP constellation that would have detections from targets on multiple platforms at the same time. If you can match locations from two detections, you will also have two radial velocity measurements that are linearly independent. We can then project this onto a level plane, or you can have 3 independent STAP detections and you'll have a certain 3D motion for your target. The same applies for a long-track interferometry. Distributed space-time adaptive processing can improve these single detections by incorporating the correlations between pulses, antennas, and satellites distributed in 2 directions. It will be easiest with formation flying, and since this has super long baselines, it should detect ultra-slow motion much better. Adding elevation to STAP can also allow for filtering based on altitude, which would be very important for AMTI. There are even more possibilities here, like inverse SAR and 3D time series, and much more. Also, in all of these distributed modes, there will generally be improvements for metrics like signal-to-noise ratio and resolutions. The main limitation of distributed SAR modes is that they will require very precise and accurate timing and distance measurements between the receive and transmit satellites and the targets. GPS can be very good for ranging and timing, especially the encrypted military signal, but it's unlikely that this could have the sub-millimeter accuracy that would be needed to not produce phase errors for X-band or higher frequencies that would ruin your imaging or STAP detection. So those central transmitting and processing satellites would probably need an atomic clock, and then they would also need super accurate ranging to all of their different receive antennas. The obvious solution for this is laser links. Because these use carrier frequencies in the hundreds of terahertz, you can have a very high bandwidth signal that will give you very precise ranging. This will also have the bandwidth needed to pass raw antenna data between the distributed satellites and the central satellite. The phase errors introduced from using different demodulation electronics on each satellite would be a much more serious problem, but it's plausible that this can be solved as well. I mentioned these central processing satellites, and these will need to be absolute beasts. Space-time adaptive processing, back projection, and machine learning algorithms all require massive amounts of compute, latency, and bandwidth. Distributed constellations like these could be producing terabytes of data every second, so downlink beams will simply not be able to send this much raw data down to the ground. Instead, you need edge processing for all the image processing and all of the detection and AI, and this is the real use case for data centers in space that I talked about in one of my previous videos. Only the final processed data of the detected targets and select images and videos would ever be sent down to the ground because of this limited bandwidth. And so building these data center satellites is going to be a real challenge, and it'll probably be similarly hard as building the actual radar satellites. Okay, so that pretty much wraps up all the tech that will be used in these constellations, and now I'll just go over a few of the implications that this will have on the military and everyday life. First up, we have jamming. There are lots of types of SAR jamming, and what you see here are different types of noise jamming. You could do wideband, which just decreases the signal-to-noise ratio, or you can do narrowband like you see on the left there. You can also send out modified chirps that match the radar, which can produce false targets and even false scenes or giant clouds of targets. The only problem with jamming is that you are broadcasting a signal from your position. These satellites are incredibly sensitive, so all they have to do is turn off their transmitters and switch to a signals intelligence mode, and they could probably geolocate the signal very quickly. A single along-track interferometry satellite could probably geolocate almost any jamming. And then if they have knowledge-aided distributed space-time adaptive processing, they could probably detect and then cancel out jamming in its normal operational mode. This brings up another implication, which is that these satellites could also act as signals intelligence spy satellites and pick up all the terrestrial signals that use the same frequencies that they do. And they could even add extra electronics to demodulate certain frequencies for radars that are super high priority for the military. When this constellation is completed, there will be a lot of implications for the military, and I think in general it would be very overpowered and really terrifying. So if any country can detect all of your radar and all of your aircraft, all of your naval ships, and all of your troop movements in real time, and also your aircraft are unable to fly underneath the radar anymore, then that is a serious problem. Also, their own aircraft wouldn't need to use their radar anymore and potentially reveal themselves, and they could track their own assets and munitions in real time for guidance. Also, they're going to choose frequencies that will work in all weather conditions, so if it's really bad weather or nighttime, then your military is going to be in a very bad situation. The best defense for the Navy would be to use mostly submarines, which wouldn't be able to be detected at the same frequencies. And then for the Army and the Air Force, you would either need to build your own constellation or have some other form of multi-static radar environment using aircraft or drones or balloons or something like this that can match what the constellation is doing on a smaller scale. And in general, this will also just be a concern for these satellites being used as spy satellites to spy on your country's operations or even just spying on citizens. On the bright side, this constellation would have lots of cool dual-use civilian purposes as well. It would be really great for science in like a million different ways, and they could use it for search and rescue and different safety things. They could use it for air traffic control, and they could also build very accurate digital elevation maps of the entire world. And so the 3D Google Maps would look way better and would be everywhere on Earth, which would be really great. So it would be really great if the military let everyone else use this constellation, at least within the United States. Although that might not be very realistic for a lot of different reasons. So in reality, we'll just have a lot of commercial satellites that are developing these same capabilities in parallel, and then we could use those for a lot of these civilian benefits. This would be extremely expensive, and I imagine it would be more expensive than something like Starlink, which is already on the order of $10 to $20 billion. But I think this would definitely be worth it for the military as long as the technology is there. So I'm going to wrap it up there. If you've made it this far into the video, definitely leave a comment and let me know what you think about this topic. Also, this was a lot of complex stuff, so if you notice any mistakes, just let me know and I'll try to put those corrections into the description. I'm also going to share all the code that I used in this video on my GitHub page, and I'll put that link in the description, and I'm going to try to do that for all my videos going forward. Anyways, I hope you liked this video. If you did, make sure to check out all of my other videos and subscribe, like, and share with your friends. And with that being said, thanks so much for watching and have a great day.